All right, it's 1:30. It's time. Thank you, everyone, for coming back from lunch through rain. I'm here today to talk about bugs. My name is Brandy. I work at Facebook, and I have brought to you a selection of bugs. I want to give a tiny bit of context here before, just to kind of give you some background on why it is I sort of have opinions on recurring bug patterns. So one of the questions I get a lot, I've been getting since I've come to CppCon, is does Facebook actually have a lot of C++? Like, don't you guys just use PHP? It turns out we have an enormous amount of C++. We've actually had enormous amounts from effectively the beginning. Facebook infra has been built on C++ effectively from the beginning. It's the second most used language behind our PHP hack codebase, and our PHP hack codebase runs on something called HHVM, which is a C++ process, which sort of lives in our repository. There's other languages in infra at Facebook. Python, notably, is definitely second, Java third, and then everyone's favorite language, etc. There's actually quite a long tail of languages. Let's see, clicker. So our team is effectively the core C++ group at Facebook. There are two groups in this group, two logical sections. One is very tool-focused, one is very code-base focused. So the tool part of our team works a lot on things like the compilers, the sanitizers, the build systems, and so forth like that. The code-based part of our team deals a lot with the core libraries, Folly. We literally have a directory called common, right? And so because of these two things, like the sanitizer is one half, the core libraries is another half, we're often an escalation point of bugs. Me personally, I'm involved often in our site event review meeting, right? So when something crashes the site, especially if it involves a C++ bug, I see it. So I have a very rich data source, right? Sometimes it's crashed the site. Sometimes it's, hey, is this an address sanitizer false positive? It's like, no, it's not. You have a bug in your code, and it's subtle, and it's here, right? And so this is my data source for this talk. So obviously my agenda is bugs. I brought some bugs with me. I had some criteria for the bugs I wanted to show you. I want them to be scary. So like a syntax error or whatever is not interesting, okay? So these are things that are scary. I want them to be common and recurring. So these are things that keep happening over and over despite our best efforts. They're also not like the list of the craziest thing I've ever seen. Okay, that's a different talk. And they're concrete. So I have bugs that fit on slides. Like I'm going to show you C++ that is broken. So it's not going to be like libraries that have bad ownership models cause lots of bugs, which is true, they do. But that's like abstract and like not super interesting. I'm going to talk about mitigation and like all the tools we have. I didn't intend for this to become like a recruiting event for ASAN, but it turns out that ASAN is actually highly impactful on almost every bug we're going to talk about today, almost every bug. So we'll talk about ASAN a fair bit, but also all the other tools. And just as fair warning, especially since there's going to be a lot of talk about sanitizers here, GCC Clang Linux bias for me, especially in the tooling part. Those of you that use other tool chains hopefully have equivalent technologies. If not, you should get some. Okay. All right, so when you give a talk about bugs, it's actually kind of terrifying because there's two different groups of people you might be talking to. One is audience number one. I show you something you have never seen before, okay? I save you from a terrible day with any luck, like if I'm interesting enough for you to be paying attention, right? So I'm hoping I show at least everybody one thing that they've never seen before. If you've seen it, you forgot, and maybe we'll flesh it out a bit. For some of you, like if you're a student or something, maybe I'm going to show you a bunch of stuff you've never seen before, and I might save you like a week, like the worst week of your career, right? Audience number two, I'm going to show you a bug you've seen 100 times. Almost always you see other people making. You're the one in the code reviewing, oh, whoa. There's something you don't understand here. And of course, if you're an audience number two and you're an expert, you never make these mistakes yourself. Never. It's never happened. But you and I are having a slightly different conversation. So our conversation is, why do these keep happening? What can we do about it? Can we fix the language? Can we make the tools better? Can we do education better, right? What can we do about it to make some of this stuff go away? All right, so enough gibberish, enough philosophy. It would be intellectually dishonest to not mention the single biggest cause of bugs at Facebook, okay? It is like the square bracket operator of a vector, okay? And I put a bunch of stuff in this bucket because, like, frankly, C index operator is the same thing, and frankly, pointer dereferencing is roughly the same thing. This is the single biggest cause of problems in probably every code base, right? It's the most important bug most of us have. But for today's purposes, I'm going to declare this uninteresting, only for today's purposes, okay? And the reason I declare it uninteresting is it's not really a C++ like self-inflicted wound. Computing has this problem in general. Every language is built or not built around it. And so I think this is actually a hard inherent problem in what we do. Most of the rest of the things I'm going to talk about are not really inherent. They were self-inflicted. So yeah, if you want to crash the site, like don't check the bounds of your vector. Start indexing into it. You'll definitely crash the site eventually. Or better yet, iterate through 2 vectors and assume they're the same length, right? So mitigation. So we'll practice now. We'll practice mitigation. I've declared this uninteresting, but let's talk about it. Static analysis has been studying this problem for a really, really, really long time. It's sort of the queen mother of hard static analysis problems. They've made a lot of progress, but the good static analysis to find this is expensive. Interprocedural, et cetera, et cetera. A lot of languages, and C++ is headed in this way, change the abstractions. You don't want to do for loops. You want to do range-based algorithms. If you do range-based algorithms, oftentimes you can hoist any bounds checking outside the loop, right? And of course, you can do things at runtime. You can literally bounds check every single array access. This is what like Ada does and has done for a really long time for safety. But as far as I'm concerned, at least in C++, your best chance of finding these is address sanitizer. Address sanitizer was built for this. If you really, really, really don't want out-of-bounds problems in your code, you need to have fuzzing with address sanitizer. I'm not going to talk about it. There's many talks to go talk about this particular problem. But if you take nothing away from today, what you need to take away is fsanitize equals address, okay? Clang and GCC, again, specific. But address sanitizer is probably the most important thing that's happened, at least in our tool set, in a long time. All right. So bug number 2, the greatest newbie trap, in my opinion, I'm nominating, in all of C++. I'm curious, by the way, before I tell you what it is, if you have a personal nomination and you think you've got me beat, come find me after. I want to hear what you think is the greatest newbie trap in all of C++. In my opinion, the greatest newbie trap in all of C++. So again, before I do the big reveal, I'm going to sort of increase I'm going to put these in chronological order. So this is sort of the order in which you will probably encounter them in your career. So hopefully many of you have seen this already. We'll end on something a little more hard. I believe it to be maps operator, square bracket operator. Ooh, I heard whispers. Yes, I've called it out. So I hope most of you know where I'm headed, but if you don't, let's be clear. Map has this property that, so in this case, I've set hey to 12 in my map. And then I try to print it out and I typo it. Okay, I've typoed it. So I'm trying to print out a key that doesn't exist in the map. Most of us know what happens here. It prints out 0, right? And you're used to that. That seems normal to you. Show this to a programmer that doesn't know C++ well and ask them what they think this does. The actual answer was like no higher than 3rd on their list. This doesn't crash. This doesn't print out uninitialized memory. This doesn't throw an exception. What this does is print out 0. And it actually inserts something in the map. So the size of the map at the end of this is 2. Okay? If you don't think that's weird, you've been doing C++ for a really long time. Yes. We won't think twice about using this. This is an occurrence count, right? Like a really dopey small one, right? Like loop through the string, and in my map, increment for every character I see. Okay? You might write something like this. The Java version of this is horrible, because you have to like initialize your variables, right? And C++, it just gets kind of, the integers get initialized. They just get initialized somehow. Don't let a beginner C++ programmer stare at this for too long. They start asking really complicated questions. Like, wait a minute, you don't initialize any of your ints. Nobody sets anything to 0. How does that work? Does that work with normal ints? No, it only works because of value. Oh, I don't want to talk about value initialization. Right? Not with someone who's falling into this trap. I want no part of like, well, see, it's like a default construction of an int, even though ints don't have default. Okay, never mind. Just next slide. Okay. So we actually protect our sort of beginner programmers from this because we drill into them const correctness. Be const correct. It will save you from bugs. This is one of those bugs it saves you from. This code will not compile, okay? You have a settings map that you're trying to read from with a square bracket operator, but the settings map is const, so this won't compile, okay? Because the settings square bracket operator might need to insert. Therefore, it won't work, right? Oh, yeah, I ruined my own joke. How does a newbie fix this code? If you paid attention, you know. How does a newbie fix this code?
Remove const.
Yes, remove const, thank you. Yeah, you remove const. Guess what, it works. I know he told me to be const correct, but it works. Yeah. So I was sitting with someone who was struggling with something else. They were relatively new to Facebook. I saw code that was exactly like this, and I said, whoa, why is this not const? I already kind of knew why. And they're like, well, it doesn't work when I put in const. I'm like, yes, let's put it in. Let's look at the error message. This is the error message. Error passing const standard map, as this argument discards qualifiers. So as a C++ expert, you know what that means. You can interpret that. A newbie sees error passing const. Like, right? The error literally says, there's an error passing this const map into this thing. So I should remove it. It works, right? Now, of course, only newbies fall for this mistake, right? Of course. Twice, as far as I know, major site incidents have occurred in exactly this pattern. Very experienced C++ teams had a widget. In this case, it was like a service handler. As in its constructor, it took a map of settings, which is already gross, right? And they assign the data member settings to the settings that gets passed in, and then they print their settings. Server initialized with timeout, whatever. Well, what happens in a refactor if you pass in a map that doesn't contain timeout? Well, we've just helpfully, in our print statement, set the timeout to 0. In most socket libraries, a timeout of 0, infinite. Yes? So this is a really excellent way of making, like, one service is dying, and now this service, all of its threads are in infinite timeouts, right? But of course, everyone tests all their timeout code paths really extensively, so this doesn't no. Okay. All right. So here's the bad news about this newbie trap. It's actually the one we're the most powerless against. I have nothing to help you. I have nothing. Like, people have legitimately suggested we just ban it. Just ban the square bracket operator of map. Const correctness helps to some degree, but not always. So I got nothing. If you have a clever idea, let me know. Come find me. Okay? I'm interested. What? Well, call at. Yeah, but so that's good if you know that, but they don't. People complain about at for different reasons. That's a different topic. Okay. So good. At is one solution to this problem. He mentioned at, because at will throw if the key's not there. Most languages have an equivalent, or rather an alternate mechanism, which is extremely common, which is this sort of get with default. So you can call a const map with a key, and if the key's not there, instead of throwing, return the default argument. C++ doesn't have one of these. Turns out it's actually kind of tricky, right? And this is the official actual implementation in GHC Haskell of this exact idea. This is a real programming talk now. We have Haskell in this talk. We've put away the toys. This is Haskell now, all right? Welcome. This is the actual implementation in Haskell. It says find with default. Default, KM, they're in reverse order in Haskell, okay? It says look up the key in the map. If you find it, or rather if you find nothing, return the default. If you find an X, return the X. That's what it looks like in the Prelude, or rather in the GHC standard library. This is what the Folly version of this exact thing looks like. So we have this effectively the same function in Folly. It's not super fair to compare this because most of that noise is type information, and Haskell has type inference. But this is a template that takes a map and a key, and the code down at the bottom is really like what you'd expect, right? Find the key. If it's not the end iterator, return it. Otherwise, return the default. That's what the sort of last two lines look like. It's very straightforward. There is something in this slide that C++ programmers hate. They hate it, they hate it, they hate it. Okay? Oh, I love this, man. Okay. So I had a whole separate slide to build it there, which is I moved all the template noise to make it more obvious. I said, let's get rid of all the template nonsense, and I said, let's just do the string version of this. So this is the exact same slide, except with string substituted. So I made it much more obvious now. It returns a string by value. That means there's a copy here, an unnecessary copy. And when I was proposing this talk and I was saying, hey, give me ideas for bugs that have been recurring, so many people mentioned, oh, having extraneous copies is a really common bug. Oh, it is, isn't it? Well, how do you fix it if you hate extraneous copies? Easy, right? We know how to fix it. We return a reference to the string. This works great if the key is in the map. I don't have to copy the thing out of the map, right? I don't have to anymore. I'll just return a reference to what was in the map, and there's no more extra copies. This is hopelessly broken. This code is hopelessly broken. Do not copy and paste this code, okay? It turns out, right, oh yeah, this code is hopelessly broken, yeah. Congratulations, we just crashed the site. It turns out that people love default temporaries. They love default temporaries. This is, in fact, the way this function is almost always used. On the right, you're creating a default string, and if you return that by reference, because the key is not in the map, v is now a reference to a temporary that has now been destroyed. Yes? This patch that I just showed you has been submitted like 4 times, and I've rejected it 3 of those times. One time, I shouldn't say someone rejected it 3 times. One of those times it got in, and we're like, oh, no. I need to do like negative caching of diffs and say, if anyone submits this diff, just auto-reject it, okay? People want to make this change so badly. But this is a broader class of problems, right? This is a much bigger problem that's well known, right? And there's many creative ways to do this, to pass a temporary to an object and then somehow return a reference to it, to the caller, right? And this is a really hard problem to fix, I think, in the language. There's some library tricks you can do often to make it harder to do this. But at some point, the language has to fix it, and I don't know if it can or will. But it can be mitigated. So again, address sanitizer catches it cold. The only problem is you often need this extra flag. So default address sanitizer, at least up to some point, didn't have this on by default. I believe it's now turned on by default in trunk. I don't know which version that's actually going to ship in. But when I turned it on, I had to add this flag. And when I turned this flag on for ASAN, we found dozens of bugs of this form, dozens. It was bad. All right, bug number 4. So this is intermission. How are we doing on time? So the intermission is interesting because I wanted to tell a story that worked. So this is not a recurring bug. This is a bug that is not recurring. This is a bug we killed. It was horrible. It was constant source of fighting. And like, we actually fixed it. It involves the worst keyword in all of C++. Who knows it? Auto. Oh no. What else? Go-to. Oh, that's a good one, but no, not go-to. What else? Volatile. Volatile. Oh. Who knows what volatile does? That's an honesty check. Oh, look at all these liars. Okay, I'm just kidding. Yeah, volatile's a really scary one. Lots of people think they know what it does, at least historically, and use it really, really wrong. Really, really wrong. We introduced what is actually in practice a terrible idea. Like, we throw a paragraph at you if you write the word volatile. Like, our linter literally spews a paragraph of gibberish at you. It's kind of mean, but that's fine. It's not actionable, which makes it a terrible lint rule, but I don't care. If you use volatile, I'm gonna lecture you. Almost every use of volatile in our code base had to do with threading and trying to synchronize threads. Now, there are legitimate use cases of volatile that don't involve threads. They just don't exist in our code base for the most part. So you might live in a code base where you actually have like memory mapped IO and you need to do volatile. But we don't. So I had a really bad lint rule by most lint rule standards, which said if you write the word volatile and it's not in a comment, I'm gonna lecture you on your diff automatically. This like really angered a lot of people. It was fun. You would get a post that was like, actually, I'm using it correctly. You have one thread, and there's a Boolean, and he's writing to it, and then the other thread's trying to read the Boolean, and I don't want the compiler optimization, so I make the bool volatile. We've been doing this for 20 years, this kind of stuff. And we had so many of these arguments, but the thing that's interesting is we won. We won the arguments. Like, people who've been at Facebook for a few years, they don't remember volatile arguments. The great volatile wars of like 2010, they're gone, 2011. Right? People stopped using volatile for threads. And I think if you pause for a second, it's kind of interesting, like, why? How did that actually happen? It turns out like people wanted atomic flags or mutexes or higher, yet higher order abstractions. And once we started giving it to them, somehow volatile just vanished. And we sort of trained the old guard who had learned. But the new people who wander into the language must be just finding what they want, the right thing. The use of volatile as synchronization mechanism seems to have mostly vanished. And I'm not exactly sure why, but I think it's an interesting case study in sort of people really want to do X, and they'll find a way to do X. And if you just give them a solution, they'll use it, turns out. Yeah. All right, bug number 5. This is the worst question in all of C++. This is the one that makes my blood run cold. The way this usually works is someone posts in our internal group. They tell a story. The story's always the same. It goes like this. We've been having an intermittent crash for like a month. It's really hard to reproduce. I can't reproduce it. What we've ended up having to do is bisect it in production. We build a binary. We run it for 6 hours. If it crashes, then that's bad. And if it doesn't, that's good. And we've been bisecting for like 3 weeks. And we finally found the diff. And we don't know why this diff is broken. We've been staring at it and ripping it apart, and there's something here we clearly don't understand. But we finally came up with a hypothesis. And then they ask you the question. It's only 3 words. Is shared pointer thread safe? Yeah, is shared pointer thread safe? What's the answer? No. I like that. Any other answers? I'm sorry. I couldn't hear. It's not this. Yeah, so you'll hear answers like this, like yes, no, it depends. People love this answer, which is totally useless, but true. It's exactly as thread safe as a normal pointer. Technically true, but useless. If you go to Google and you type in is shared pointer, the top result is shared pointer thread safe. By the way, the third result, is shared pointer slow? No, shared pointer is not slow. If it's in your profile, fix your code. Is shared pointer null is 4th? Yes. Your shared pointer is null. Put a check in. Okay. But we're here about thread safety, all right? Is shared pointer thread safe? So I've had a lot of time to come up with an answer. I have a lot of practice. I believe the answer to is shared pointer thread safe to be no, okay? That is technically, I believe, to be a lie. But I'm answering a slightly different question than the one you're asking. You asked, is shared pointer thread safe? But what you meant to ask was, is my code correct? And the answer, if you have to ask, is no. No. So here's my teaching side. So you might have no idea what we're talking about. You might be in audience 1 right now going, what are these people talking about? What do you mean shared pointer isn't thread safe? Let me explain it to you. A shared pointer, and this is a mental model. This is not an implementation. This is a mental model, is 3 things. There's the actual shared pointer struct, which is a pair of pointers. That's what it is under the hood. And it doesn't have to be, but in our mental model, that's what it is. It points to 2 things. One pointer points to the shared t. One points to the shared reference count. This is where like the C++ people get really uncomfortable. They're like, oh, it's not a reference count. There's a lot of other stuff in there. It's technically called a control block, and it contains, weak pointer. But for mental model purposes, it's a reference count, okay? And the answer, or rather, when you copy it, all you do is you copy the struct with the 2 pointers, and they point to the same 2 shared things, the shared reference count and the shared t, and you increment the reference count, right? That's how shared pointer works under the hood. That's the mental model. The thread safety kind of approximately looks like this. Anything that touches t is unsynchronized. The shared pointer will not help you synchronize the t, okay? That's on you. If you want synchronization at your t, do it yourself. The shared pointer will, however, manage the control block, and in particular the reference count. So if multiple threads destroy shared pointers, they will both atomically decrement a reference count. That will happen. But the one that trips people up tends to be this thing on the left. For some reason, people want to read and write to a shared pointer unsynchronized. It doesn't work. For the exact same reason, a pair of pointers wouldn't work from 2 threads. This is a thing that for some of us seems super obvious. So I was like testing this with people at Facebook. Like, do you know this? Is this obvious? Does everyone know this already? And one person literally went like, that's the crash. That's the crash. We have a map and there's shared pointers, that's the crash. I was like, okay, I guess it's going in the talk. Yeah. I've changed the definition of the colors now. I want to talk about our intuition now. So now I'm moving towards audience 2. You hire lots of programmers and you're training them over time. You should know this about their intuition. They get the right-hand side correct. They naturally assume that T is unsynchronized when playing with shared pointers. That they get it. It's just intuitive. They naturally assume that the control block, the reference counting, happens for them automatically. The thing they seem to get wrong is the one on the left. People really want to read and write to shared pointers unsynchronized. The pattern that comes up over and over and over at Facebook, and I think this is an artifact of the fact that we write a lot of services, is this, it's a buggy form of RCU, and it's actually a degenerate but very common form of RCU. RCU, by the way, is read, copy, update. It has a Wikipedia page. There was a talk about it. I'm not going to talk about it too much here. But in our most common use case, it's actually very simple. You have a service, it handles requests. You have one thread who's responsible as the updater. So one thread wakes up every 20 minutes or whatever, goes and reads some database, populates some in-memory efficient version of whatever's in the database, and then stores that into a shared pointer as the one true most recent state in the universe. The worker threads go into that one true shared state at the start of their response. They pull one out, grab a reference count to it, and say, okay, I'm going to use this state of the universe for this request. And then on the next request, I'll grab a new state. So you won't update me whilst I'm in a request, but I'll pick up the update after I'm done. And this has a lot of lovely properties in a service, right? Because updates are really cheap. You're not really blocking anything to do your update. It has the downside, of course, so that you may have multiple states in flight, right? Like whilst you're updating one state, someone might be using the old one, and you've got to be able to tolerate several states like in memory at once to have this work effectively. But the implementation here is actually really easy. Like all you got to do is at the heart of that handoff, like have a shared pointer and a mutex, and like have an atomic get and an atomic set, and like you're done, right? It's not even that. It's literally like the easiest thing to write. But what's interesting is our intuition fails us. People keep writing the wrong thing. And then they have a really bad month. Like finding that bug takes a month if they don't see it or know it. So mitigation, yeah. So thread sanitizer finds this if you run thread sanitizer. Address sanitizer often finds it as well, but it's not super helpful. Because what ends up happening is you end up corrupting the shared pointers and you destroy the wrong thing, and it looks like memory corruption, and it's not always clear. Address sanitizer will tell you something's wrong, but it won't necessarily aim you right at it. Now we get to the libraries part of the talk. There has been a thing called atomic shared pointers since C++11. On paper, this solves the problem. Of course, most implementations haven't had one. And then there was a concurrency test that added atomic shared pointer like this. There's atomic shared pointer like this, and then like this. And then we went back to atomic shared pointer like this. Like I heard something about a vote in Toronto. I asked someone in SG1, so I tend to hang out in the evolution working group of the committee. I don't really hang out in the SG1, which is where they talk about this. I was like, can you give me the history of this? Because I'm going to give a talk, and I'd like to at least tell people like what the deal is about atomic shared pointer. And they're like eyes glazed over, and apparently this is like a big, long, interesting, I don't know about interesting. This is apparently a big, long topic of back and forth of what's going to happen with atomic shared pointer. I don't actually know its current state. I suspect we'll get something like it at some point. It does solve my problem. But to be fair, I don't need a highly performant atomic shared pointer to solve my problem. I can get away with a mutex and a lock. And in fact, there is also another proposal, if this is interesting to you, about a cell type of an abstraction, which is effectively exactly what I want. It's also before the committee. Oh, bonus bug about shared pointers. We have this one all the time, too. I don't know why people write this. I can't explain it. Some function returns a shared pointer. They just dereference it immediately, and they grab a reference to whatever's at the other end. And now you call reference.boom. So the problem here, of course, is everything that happens after that, the shared pointer's gone. It's been destroyed because you dereferenced it. And you don't have the protection of a reference count anymore, right? So all your code is now running without a reference count protecting it. So this one's come up a number of times. But again, address sanitizer does catch this one very easily. All right, let's see. All right, my last one. This one's my favorite. Bug number 6. This is code review. This is going to be interactive, at least a little bit. I'm going to show you a series of slides with very little code on it, very little code. And I have 2 questions for you. Question 1, does it compile? Everyone's favorite C++ game. Will this code compile? Question number 2, if it doesn't compile, what error message would you expect or even like if you're being ambitious? Okay, so does it compile? What kind of error message do you expect? Here's the code. Include a string, void f, standard string, parenthesis foo, close parenthesis, semicolon. Raise your hand if you think this code compiles. So for the purpose of the audience, maybe 10%. But I pointed that because that's Richard Smith right there. You're what, the editor of the C++ standard, right? Yes. The editor of the C++ standard says this code compiles. Who's changed their mind? Richard, unsurprisingly and surprisingly, is correct. This code compiles. Almost everybody in here got it wrong. This code compiles. What? Okay, so take a minute. Pause the video, if you're on video. Think really hard about how this code could possibly compile. And then think a little bit more, more existentially. Like, what are we doing? And why are we here? I feel like I'm wasting my life a little. Okay, this code absolutely compiles. And the answer, and I'm not an expert in the standard, but my understanding is the way the standard works, at least in this part of the standard, if something looks like a declaration, it is a declaration, no matter what else it might be, right? And that looks like a declaration. So this and this are basically the same line of code. Those parentheses are optional. So what you're seeing in the top is a declaration of a string called foo. Okay? Now, that seems like trivia. That seems weird, okay. Here's me proving it. By the way, so you put it into Godbolt, and you can't really see this, but what you'll see in Godbolt with no optimizations is the default construction of an empty string, and then the destruction of the string. So you'll see the creation and destruction of an empty string foo. So, okay, but the question becomes okay, so what? How is this possibly one of the most common and horrifying bugs in all of C++? And I posit to you that it is, just not in this form. It's in a slightly different form. And this is often what it looks like. You have an object that has an update method, and this object is meant to be used from multiple threads. So it needs to be internally synchronized. And so you, of course, have a data member that's a mutex, and on any mutating method, you have to lock your mutex, right? That's the way it works. So you lock your mutex, and then you do the mutation, right? Do you see? Everyone sees the bug, right? Do you see it yet? Who sees it? Only half of you, okay. Yeah, so I didn't name my lock here, right? I am not, that unique lock is intending to be like a lock guard, right? I'm intending to, on construction, lock my mutex, and on destruction, unlock my mutex. That's what I'm hoping this code does. That is not what this code does. No, what this code does is it declares the existence of a unique lock named my mutex, and that shadows the mutex data member that you were trying to lock. And to be clear, nothing gets locked. There is no lock that occurs here. It looks like it's locking what you want it to lock, but it's definitely not locking what you want to lock. And the fix is super easy. You've seen it a million times. You have to name the lock guard. You have to give it a name. Now, this is a unique lock named G, whose construction locks the mutex and whose destruction unlocks the mutex. So your code is now protected by a lock guard, right? Do a code search for this. This is the pattern. Do it. Unique lock of mutex. If you have a code that's using relatively recent C++, do a code search for unique lock of mutex. GitHub search won't let me do it, so I couldn't do it on GitHub. But I figured since I'm giving this talk and I'm telling all of you to search your code, I should search mine. Do you think I found a bug? Yes. This is what the actual code looks like. Standard unique lock of standard mutex, parenthesis mutex. That is not doing what it thinks it's doing. That is not a lock guard. That is a shadowing unique lock that is not locking the mutex it tried to lock. I didn't just find one bug. I found 2 bugs in our code base. And here's the sad thing about this. I only found 2 bugs, which is okay, but we actually have a lint rule to protect against this. So this is 2 bugs that got into our code despite the linter telling them not to do this. Imagine how many we would have if we didn't have a linter telling people not to do this. All right, now we're going to do the worst C++ quiz of all right? And I've taught you everything you need to know. There's no more tricks. I've taught you everything you need to know to understand what happens next, all right? So does this compile? So remember, this compiles. This compiles. Shockingly, perhaps, this compiles. Does this compile? Raise your hand. Does this compile? If it does this compile? Yes. Ooh, only half of you. So this compiles as well. This compiles as well. The first one, as we've mentioned, is a declaration of a string named foo. The second one is a constructor. It constructs a temporary string from a char star. All right, let's make it worse. Does this compile? I wrote it twice. It's copy and paste. Raise your hand if you think this compiles. No, this doesn't compile. No, this is a redefinition error. This is a redefinition error, because if it looks like a declaration, it is a declaration. So this is the same as writing standard string foo. It'll say you can't declare the same variable with the same name in the same scope. So this is a redefinition error. All right, does this compile? Look closely. What? We have a question. So it could be interpreted that way. It could be interpreted that the second one is a copy of the first. But the rule is if it's ambiguous and it could be a declaration, then it is a declaration. So this is a redefinition error. To be clear, I'm slightly out of my league here, because now you get into like super parsing of the standard. But as far as I tested, nobody will compile this, and I believe that's why. Because the rule says if it's ambiguous with a declaration, then it is a declaration, period. And that's why you get a redefinition error. All right, does this compile? All right, yeah, most of you have got it now. Yes, this does compile. Okay, so the first one is a declaration of a string named foo, and the second one is a temporary copy constructor of the string. It's just calling the string's copy constructor with the first foo. Just, okay, all right. And then finally, just for symmetry purposes, you grab the squiggly braces and you pull them out. Does this compile? Yeah, all right, most of you, yes. So most of you say, yes, this compiles. And so the reason this compiles, this is again, a second declaration of foo, but it's now in an inner scope. Okay, so those squigglies are a scope, and it's now shadowing the outer foo. You have two declarations of variables with the same name, but one of them's in an inner scope shadowing the outer one, right? That's what's happening here. So this works. So some super important notes. There's actually a subtlety here that's critical to understand. There are two things that make unique lock conspire to have this really pathological bug-prone behavior, as far as I'm concerned. The first is that it's RAI type, okay? If you have the exact same situation with a non-RAI type, you tend to notice very quickly, because you didn't name it or anything, so you'll like try to use it or something, and you'll be like, whoa, okay, I forgot the name. But RAI types, their mere declaration is often all the functionality. That is the functionality. I declare it, right? And then that means I've got one. So you're much less likely to name it, because you don't actually need a name. You never need to reference it, right? The second part that's actually really important is this only works because standard unique lock has a default constructor, right? Because I default construct mutex in this case. I have to use the default constructor. So unique lock is affected, but lock guard is not. So if standard lock guard will not compile in the case of, if you were to swap that out. Now, if you're using standard types, that's great, because standard unique lock has this weird property. You can lint on it fairly easily. If it's like our code base, you have like lots of reimplementations of lock guards from the years, right? Like dozens of them. And very few people like fully appreciated this problem. So we found, I don't know, tens, maybe 100 cases of our other lock guards that did have default constructors being bugged in this fashion. So if you have a lock guard, I like run, don't walk, to see if it has a default constructor, okay? And by the way, unique lock does. C++17 has a thing called scope lock, and it's entirely unclear to me if it suffers from this problem or not, because it's complicated. As of yesterday, when I put it into Godbolt, Clang will not compile it, and GCC will. I'm not sure. So scope lock may or may not have this problem in C++17. So anyway, the TLDR on all this is, if you have an RAI type and it has a default constructor, you're in a very dangerous situation, potentially, where people will try to wrap something and forget to name the object, instead of what they're wrapping, and they'll end up declaring a shadowing thing, okay? So this is my other takeaway for you. All right, so mitigation. So W shadow is at least in GCC and Clang, is a warning that's been around a while. It absolutely detects this, W shadow. So shadow tells you about shadowing warnings. That's when you have like a variable in an inner scope that shadows a variable in an outer scope, it will warn you. And if you put this particular pattern in and you turn on W shadow, it will absolutely find this bug. The problem, of course, if you've ever used W shadow, is it's extremely pedantic. It almost always gets turned off. It's full of noise and things that you probably don't want to fix and makes the code maybe worse. There have been these hybrid flag suites. So there's shadow compatible and shadow compatible local. These are meant to be much higher signal versions of W shadow. So shadow compatible only will tell you about shadowing warnings if the two types are compatible with one another. And shadow compatible local is only if they're local in the same function and they're compatible with one another. I strongly encourage you to turn on at least W shadow compatible local. You will find all kinds of, if not broken code, like smelly code. Like there's an outer loop using I and a bunch of inner loops using I, and it's like, let's not do that, right? Even if it's not bugged, you don't want to do that, right? So shadow compatible local is good. You should turn it on, but it does not catch this. Only W shadow catches this bug. So I'm sorry. The story there isn't great. But that means this is easily detectable, right? Our extendable Clang-based linter has a check for this. It's actually fairly easy to detect, but it's actually not widely detected. If you don't have a tool that finds this pattern, which is to say like unnamed lock guards, right? That it sort of immediately wink out of existence, I suspect you have a lot of these, especially if you have default constructors on your lock guards or you use unique lock in your code. So again, I'm not exactly sure what the best, so I have some extra stuff here that I didn't want to get into in too detail. There's a related class of problems which isn't this declaration issue, but it's more like you create something that exists for one line of code only when you expected it to live forever. And that's a place where like a no discard attribute for constructors might be helpful eventually. So there's like two flavors of this, but the more common one is the declaration one. So again, we have a Clang-based linter, so something like Clang tidy, for example, could very easily find this. All right, so conclusions. C++ is hard. That's not fair. It's kind of a value judgment, but we should just admit it, I think, okay? C++ is hard. Like a lot of this stuff here, we've had some of the best C++ people like spend a week finding a bug and at the end track it down to like their lock guard is like missing a G, right? And like, that stinks. And the consequences of that are really, it's a painful thing to debug. It's an incredibly painful day to find that bug. And it's a one character change, right? The patch is one character. Tools are our best teaching weapons. So lectures are great. I would love to like put every Facebook programmer through a lecture that just taught them about all the bugs that they should never write. Like, doesn't actually work all that well. The sooner after you write the bug I tell you, the better. Like, right? Everyone would pretty much agree with that, right? If your IDE tells you just wrote a bug, that's fantastic. If the compiler tells you just wrote a bug, that's pretty fantastic. If your diff review tool runs some expensive asynchronous thing and comments on your change set and says, oh, that's definitely a bug, that's pretty good. That's pretty good. If you get an email 2 days after you committed it because some monstrosity, like some supercomputer did some interprocedural static analysis and emails you a bug, that's still not terrible. Not great, but not terrible. If I have a talk like this and like 2 years after you spent a week debugging it, I explain it to you, that's like borderline useless, right? So really, like for a lot of this, for my money, I want better tools, right? And I'll talk in a minute about this, but the sort of Clang extendable linters have been really powerful internally in terms of, for a particular data type, having specific rules we can check, checking certain kinds of semantics. I don't want lock guards that shadow mutexes, for example. That's a really good rule. Clicker. Yeah, I just said this. So yeah, extendable linter. So Clang tidy is an example of this. We have one internally called how to even, because you can't, they're clever. They're clever. Okay. And address sanitizer. Yeah, like I didn't really intend for address sanitizer to be the solution to all of my problems in this talk. It just worked out that way. One cannot speak highly enough of address sanitizer and the amount of bugs that it finds in a code base. If you live in a code base that compiles with Clang or GCC and you've never turned address sanitizer on, leave. Go do it right now. Go to one of the desks. I hope all of them are turning on address sanitizer right now. It's really, it's life-altering, right? You'll find a dozen bugs in your code base, right? Running your test suite with address sanitizer turned on for the first time. And don't tell anyone until after you've asked for a raise. But then teach your team about address sanitizer. You're welcome. Okay. Questions? I'm done. If there's no questions, I'm going home. All right. No questions. Oh. No.
What bugs didn't make the cut?
What bugs didn't make the cut? Everyone kept trying to say unnecessary copies. And I was like, I have a huge bug that I keep having because you all hate unnecessary copies so badly. So that one didn't make the cut. A lot of people want to do small things like pass by reference instead of pass by value. I'm just going to pick all the ones Nicholas just submitted a few minutes ago. The other one that's really common, so I actually think one of the most important bugs in C++ that we haven't talked about that's actually really hard is asynchronous programming and lifetimes. So we have folly futures and we have fibers, and we have a lot of lifetime problems related to asynchronous programming. And other languages that have solved this, that have asynchronous programming frameworks, have garbage collectors, which help them with all the lifetime issues. So we have a lot of problems related to that. That was a very popular nomination, but we didn't, it doesn't fit on a slide. But I do think that one's actually really critical. Asynchronous programming and coroutines will help with this, and lifetimes become a really tricky balance. So that's a short answer. Okay, who's next?
Early on, you had a slide about a diff that people kept wanting to submit on your get default.
Yeah.
Why wouldn't you put a comment there saying you might expect this to be this, but don't do it?
Yeah, so I have a skipped slide. Well, I won't go to it. No, what we ended up doing was making a overload to that function that takes the R value default and delete equals delete. That solves most of the problem, and then put a big comment there. That's what we ended up doing. The actual more complicated lie here is that the more complicated truth from the simple lie that I told. We had more than one of these. So the folly one we fixed, but there was a different one in our STL utils that was some ancient code, and that one had a bug in it that got committed without us noticing. So that's what happened.
Will return an optional to a value save map index operator?
Will returning an optional from the map index operator?
Return an optional to a reference to a value. Will it save this index operator?
Yes. Yeah. So square bracket operator on map returning an optional on a const map. So I don't hang out in library, but my suspicion is that that particular thing is, everyone would like something like that eventually, and it's complicated for reasons that, optional is another good one. Just corner a library person and ask them about optional and all the ways that it gets hard. But yes, I agree. That's what Haskell does, right? It returns a maybe type. So that's what you want. You want an optional as your square bracket operator. So I agree. That's the right direction to head in eventually.
Thank you.
But standard optional doesn't support references.
Someone who would know better than I, yeah.
So my actual question is, will C++ 17 rules regarding mandatory copy elision simplify or complicate the concerns about too many copies?
I don't know. What do you think?
That's why I asked you.
I think we're rightly worried about copy. So mandatory copy elision is good. I just, not all APIs, especially ones that take references, can return references, right? That's part of. I don't know. I don't think so. I think copy elision is good. On average, it'll be good. I think the broader problem of it's really easy to smuggle a reference out of a function is its own problem. I don't know how or if we can fix it. Do you think we can fix it?
I'm wondering if people will be less scared about returning copies so we just don't run into the problem. Or if we start talking too much about is this copy getting into a more complicated space for the language.
Yeah. Well, so in the example of get default, you have no choice because you have more than one source. So you can't elide the copy, right? If it's in the map, you have to copy it out. So in that case, it won't help. But on average, you're probably right. It'll make it much less likely for people to be paranoid about copies. Dimitri.
These linters looks really useful. Do you have plans to open source them?
What looks?
Linters, like Clang based.
So we built, this is a long story too, we built how to even, which is effectively Clang tidy, right before we had a Clang tidy that we could use. So we sort of built our own version of this thing, and there's been great long-term discussion of like, if we open source it, are we just bifurcating the space? Should we convert all these checks to Clang tidy checks and go that way? So this is an ongoing discussion. Yeah, I want to open source stuff. Like we should open source all these tools, and we often do, but we gotta figure that out. That's the real issue. Like this, it really is just a simpler version of Clang tidy. That's what it is. So I'm not sure how valuable it would be in its current state.
This is more a comment for the audience, actually. So when Facebook copies 100 bytes too many, it costs them $1 million. Me and you, it costs 0. You have so much bigger problems than just like copying a string one too many times. I just had to say it out loud, sorry.
It's true. No, but the problem is, if you're a library author, you have users who care occasionally. And oftentimes, even the ones who do care too much. It's like, no, I don't see it in your profile, go away. But fair point. Tony.
Have you brought up the scope lock constructor?
So I've discussed this with people in SG1, and they said to do a DR, and I said,
Library,
I'm not actually
Library Evolution, Library. Talk to those guys.
Oh, okay. Yeah, yes, I've had conversations with these people, but I'm not actually sure if it's broken. Or I don't know if it's broken is the right word, but I'm not actually sure if it suffers from this behavior. I have to spend some more time. I originally thought it did, and then I was going to go ahead and do it, but then on second glance, it interacts with some other weird stuff. Because it's a variadic template, so it actually, and then there's argument deduction now, so it's complicated. So I'm not actually sure if it suffers from this behavior or not. So if someone wants to...
There's people here I think could probably answer that for you.
All right, I'll ask them. Who should I ask?
Well, you've got a few experts.
All right. I know. Poor Richard. He didn't know what talk he was coming to. Okay. Any other questions? We all set? All right. Thank you, everyone.